Today, Lex Kemper is going to talk about quantum computing meets condensed matter physics. Lex has a PhD from the University of Florida. He did a postdoc at Stanford. Then in 2012, he became the Alvarez Fellow at Berkeley Lab. And now he's an associate professor at North Carolina State, where he works on the intersection of quantum computing and condensed matter physics. Both things I don't understand very well, so I'm really excited to learn something. Take it away, Lex.
All right. Thank you, Juliana. Thank you, by the way, for organizing. It's been a nice opportunity to sort of to see, what the people have been up to, and I'm looking forward to the rest of the talks. Okay, so I'm going to tell you guys a little bit about condensed matter physics and about quantum computing and sort of the little bit that I do with them. So let me start with something simple. So this is something. So APS March meeting is our national physics meeting every year. It just happened 2 weeks ago. And there was a phrase that I overheard, which says it's not a cuprate talk unless it has a phase diagram. So cuprates, for those of you that don't know, are things that we make high temperature superconductors out of. And it has a phase diagram. It has many, and usually they look something like this. They're quite complicated. They have, they've got many phases on them. They've got the superconducting phase. They've got some charge density waves. Nobody knows what's going on over here, so I'm not even going to name it. There's a magnetic phase and this and that. And so I thought this was said as a joke, this line, but it's actually kind of insightful because really, physicists use phase diagrams to communicate, specifically condensed matter physicists, use phase diagrams to communicate with each other, right? So having this phase diagram on sort of tells you, well, if you're a condensed matter physicist, what the material is, what the physics is that you're interested in. Well, you might be talking about charge density waves, right? So this talk was probably about charge density waves, which is the CDW. And so you're using this to communicate what physics you're looking at. We like to know what the phase boundaries are. We can tell from this phase diagram something about the material. It's got magnetic things, it's got superconductors. In this case, they don't overlap, sometimes they might. And so these contain a lot of information. So we use them a lot because really phases of matter is sort of what we care about. Now this one might be complicated. So let's do an easier one. This is the phase diagram for water. It's got pressure on the vertical axis, it's got temperature on the horizontal axis, and normally, let's see, we live somewhere around this pressure because we can go from the solid phase, known as ice, to the liquid phase, known as water, to the gas phase, known as steam, so we sort of sit there. And there's multiple complicated phases of this. Now, I'm originally Dutch, and we have a lot of ice, and oftentimes this is your first exposure to ice as a small Dutch kid. You get to go on the ice, maybe not anymore, but when I was young, you could. And really, ice is ice, but ice has a lot of phases. So question for you all, and you can put this in the chat, how many phases of ice do we know about? So make a guess. There's no negative points if you get it wrong. All right, it's 13 and 2 and 3, 20, 3. Okay. Excellent. Those are all great guesses. So here is one example phase diagram for water. And all of these phases are ice. All different kinds. So you can see the largest one on here is 15, I think. So we have 15 different phases of ice. This is out of actually, Aditi was right. The 20th one was discovered, or at least I saw a paper about this last week. So we still discover many, many different kinds of phases of ice. So I was teaching thermodynamics this semester, and I told my undergraduate students this, and they said, well, okay, but ice is ice. Like, what do you mean? How are these different phases? Which is actually, really an insightful question, because what it means to be a different phase kind of depends on who you're talking to. The simple answer is, they have different structures. I can look at ice 8 and ice 9, and you can see they're arranged slightly differently. These are X-ray data that tell you how the atoms are arranged, and so they behave differently. But from the perspective of somebody who's drawing something or who's working with this material, these might sort of be the same. And so what are the different phases is kind of sometimes they're not so different. They have the same properties, and sometimes they're very, very different. So that was water. But we have a lot more than that, right? We have the whole periodic table that as condensed matter physicist or materials physicist, we can mix and match and put together. And so what you get is you don't just get ice, but you get, I don't know, all of these things. So here are things, these are transition metal compounds made from copper and manganese. These are iron and pnictides, so pnictogens, so nitrogen, phosphorus. And they have, I don't know, all sorts of interesting phases. So these have charge order, spin order, superconductivity. This has all sorts of weird things. This is a new kind of superconductor that was discovered while I was doing my PhD. It was very exciting at the time. Right, but because of all these possibilities, condensed matter physics is really a very, very large field with lots of interesting materials to study. Now, why do we care? Obviously, fundamental science. I'm done. Right? We care about emergent phenomena. We care about superconductivity, we're trying to understand how all these pieces that you can put together in this material make these things. From water to the cuprate superconductors that I talked about. But it's phase diagrams and phase transitions are not limited to that. If you were a high energy physicist, you might care about the phase diagram of quantum chromodynamics, which has similar sort of shapes and lines and things on it, although the scales are very different. These are 300 Kelvin, and these would be 300,000 Kelvin, or 3 million. Right, and the phases have different names, but we also we care about this sort of fundamental science. I don't know if you're going to find people that will convince you that the studying things out of QCD will have some kind of practical application anytime soon. But in condensed matter, we're a bit closer to Earth, and actually we do, because I can take all of these things, right, and I can take all these elements and replace them by some application that they have. All of these things have an application somewhere in our lives, more or less prevalent, right? Nickel and aluminum are things that you find often. Palladium and osmium are things that maybe you don't find as much. And some of these things, even something simple that we understand, like a magnetic phase, like we've understood those sort of since the 50s, they're still active research. For those of you that are my age, know what one of these things is. It's a tape. It plays music. But it also stores a lot of your computational data, right? If you walk over to, actually, I don't know if NERSC still has this, but they used to have, tape storage because it's really high density. It has its own phase diagram. You can look at what the magnetism does as a function of magnetic field, all these things, right? Based on these things, we built reed heads, brick heads. This is how you played music in your car back in the day before CDs. Tape decks were a thing. And while we think of this as old technology, really the most recent patent when I looked 2-3 years ago was in 2018. So these are still being developed. We're improving our understanding on these sorts of topics. So condensed matter is something that has, a lot of fundamental science and a lot of application. And we just sort of live in the intersection of both. Okay, so that was one half of my title. The other half is about quantum computing. Okay, so before I did quantum computing, this is from my website, what I did, and I still do, is I look at quantum materials sort of in and out of equilibrium. Those are big words, so let me tell you what that means. So a material in equilibrium is, my pen that I'm holding, it just sort of sits here. But what you can do is with your experiments, right, is you can look at, say, a piece of metal or a pen or whatever with different colors of light, with X-rays, with neutrons, with all sorts of different things, so you can study them. A different thing that you can do is you can go to one of these things. For those of you that are at Berkeley, this is just across the water from you. This is the LINAC accelerator that sits at Stanford. This is SLAC National Lab. If you drive over the highway, you will drive over this. It looks like a long series of shacks. You can see it from the highway. And this used to be a particle accelerator where they smashed B mesons into each other. Now what it is it produces ultra fast X-ray pulses. And what you can do with that is you can take your material and you can sort of hit it with a hammer. It's made out of light, but okay. And what that does is it makes the electrons move and it makes the ions move. And then with experiments, you can look and see inside how they move. So sort of pictorially, what you do is you take your piece of material, you hit it with one laser pulse and everything starts to wiggle. And then you come in with a second laser pulse a little bit of time later, and then you make some measurements. Now, why would you want to do this? Well, because in a sense, this is how you learn about what something does, right? If you have a tuning fork, it's not so useful by itself, but if you hit it against something and you drive it out of equilibrium, you can learn something about how it behaves. Now, what that does is it takes, some experimental measurement. Here's a picture of photo emission spectrum, not so important. What that does is it takes this kind of measurements, which is sort of complicated to explain already, and it makes it dynamic because now everything is moving. So this is real experimental data on the real material, looking at how many electrons per second do I get out as a function of this difference between laser pulses. And what you can see is, I get lots of stuff. This bends, I get some oscillations back and forth here. I get some spectral weight that sits up here where there wasn't any before. There's a lot going on. And trying to understand this is really complicated. So the hope was, with these new fancy experiments, we will be able to study these things more carefully and learn a lot more. The price that we have to pay is that now we also, in addition to understanding some complicated material, I now have to also understand some complicated experiments. Okay, fine. So that's where I came. And one of the things that I did during my time as an Alvarez Fellow is I worked on software, numerical tools that solve these sorts of problems. Did we have Corey at the time? I forget. So just very briefly to tell you what that was, I thought this was interesting. I pulled my slides back from 2015. This is a talk that I gave here where I am now. And what I talked about, well, okay, was from that. I didn't talk in this much detail. The things that we solved using our high performance computing tools are these nonlinear integral differential equations for Green's functions. And I don't just have one, I had 6,400 of them. And so, basically what that meant is I took a whole large section of NERSC and ate all of them. I had lovely help from lots of people while I was there, including Didem, who's here, thank you, on how to sort of optimize this and how to work and actually make this something that you could actually execute. So I learned a lot from people around me. And as a result, what we were able to do were these sort of simulated spectroscopies. So we would do simulations of what you would get out of an actual experiment, out of these sorts of calculations. So, something like 3,000 for 12 hours or something like that. Okay, so this is what I did back then. I continue to do for some time. But this is not the only way that you can approach this problem. There are multiple other ones. You can do something called density matrix renormalization group. You can do exact diagonalization. And all of these things are sort of numerical tools that are aimed at trying to solve or trying to answer questions about this really complicated. As always, there's a problem. All of these techniques get stuck. The stuff that I worked on, right, like I have to, for these integral differential equations, I have to store a full history if I do the simplest thing. Eventually, my computer runs out of memory. DMRG has a similar problem. It's also only works in 1D. Exaction has the same problem, but in a different way. And so this is generally the case in condensed matter physics and a lot of other places, that eventually your computer power is just not big enough for some reason or other, whether it's memory access, whether it's CPU limited, whether it's, I need to wait for my InfiniBand, all of these things eventually run. So this is where quantum computing is supposed to help. So let me give you one example of why this might be the case. So suppose I want to do something from a physics perspective, really simple, is I want to look at the transition of a system from a paramagnet to a ferromagnet. Okay. In a ferromagnet, all the little spins are aligned, and in a paramagnet, they're all just sort of pointing in random directions. Now, the simplest way to attack this problem is I write down a functional that you want to minimize. It's called the Hamiltonian. In this basis, it is a gigantic matrix. How big is this matrix? Well, if for every spin, it could either be up or down or some complex linear combinations of that. So I can count how many states do I have? What is the length of my bit that I have to store? Okay. For 50 spins, it is that number. I don't know how to pronounce that. It's got way too many digits. The point is that it's large. And this is only 50 spins, right? Like if I have a piece of material, it's got 10 to the 23 of these things in it. So this is not going to work, right? These approaches, and this is the simple one, right? And you can reduce this by symmetry and do all sorts of other fancy things. But in the end, you will eventually be limited within this approach by how big of a thing you can store. And this is where quantum computing is supposed to help, because each one of these spins would be 1 qubit. So really, you would need 50 qubits to address the same scale of problem. And this is why people are interested, and this is why people care. Because I can't store this vector, right? It's too big. I can't store a vector of complex numbers that long, but I could have 50 qubits make. So, we had a talk about this 2 weeks ago from Jared. That was lovely. There's a lot of things on quantum computing. They're all over the news. So what I'm not going to do is I'm not going to give you an introduction to quantum computing, but I will tell you some aspects of how it intersects with what we're doing. So what it's doing for us is it's replacing my software stack. So normally what I would do is I would take my physics inputs, I would run it through some kind of software stack, and then I would get some observables out, right? Whatever I want to look at that I could compare to experiments or that I care about. What that now is doing is it's replacing either the entirety or part of my software stack. So that I'm solving the problem, on my computer that I have sitting here, I might offload some of that to a quantum computer in the same way that you might offload some of it to a GPU. And just like you would with a GPU, sometimes it's, your calculation is entirely on the GPU. Sometimes it's some kind of hybrid model that you do. The observables we care about are, these sorts of things. And I'll tell you a little bit about what some of them are, but we're having a ton of fun, looking at some of these things. So let's pick one and let's sort of see how this works. So what you measure as a physicist is a fancy word. It's called a correlation function, but it's not so hard. Really what it is if I have in my material, if I see something over here, or if I excite it with a laser pulse over here, or if I know that there is a particle at r prime and t prime, what is the probability I find it some distance later? This covers this framework covers a whole bunch of things that as a physicist you might care about. You might want to measure the conductivity of a material. How well does it conduct electrons? You might care about what the single particle excitations are. You might care about its magnetic properties. They all sort of fall into this category. So this is like a very fundamental beast for us to look at. And you can go and open condensed matter physics textbooks. And what you can find is that really what this represents is sort of, it's an interference experiment. You start in a ground state, you have it live for some time in an excited state, and then you let those interfere, and then you get your measurement out. And that tells you a lot about what's going on. For those of you that do quantum computing, this is the sort of standard quantum circuit that you have. You prepare some ground states, you let it evolve, and then you do some interference measurement and you collect that information elsewhere. But that's a sort of basic idea. So we have quantum circuits that we can build for these kinds of interference experiments on my quantum computer. So, this is sort of arcane. Let's pick a specific thing I can look at. So one of the things that map nicely to quantum computers are spin models. So here's a good spin model we can play with. And this one is called the Heisenberg model, and we'll talk a little bit about what its excitations are. If it's in a magnetic phase, all my spins like to point up. And then I can think, well, okay, what kind of excitations can I make that I can do my interference experiment with? Well, I could just flip one of them. That is an excited state. It's a bit high energy, and it turns out not to be the right one. What the right one is all of the spins sort of rotating in order. So you get something called a spin wave because it looks like every other wave that you know. In a limit that this is infinite wavelength, this costs no energy, and so we can measure, what is its energy as a function of momentum, and that's all good. So what we thought is to try, just to sort of get started with the whole, applying quantum computing thing, was to try and measure this kind of a thing. And naturally, the thing to start with is 2 qubits, because 2 is sort of the minimum for this sort of thing. So we did that. I'll talk you through what this graph is. So we started with our ferromagnetic states. We flipped one of them, and then watched how the system, watch how it rings, right? Watch how the excitations move. Watch what their frequencies are. In this kind of a system, there's only one frequency. There's a bunch of frequencies. But what you get is if you do the exact calculation, these nice wiggles. These are different correlation functions you can measure. And the blue dots and the orange dots are what we got from the quantum computer. This was back in 2018 or so.
Yeah,
so I thought, oh, great.
Alex, can I ask a quick question? So,
hey, Len, sure.
Hey, what does 2 side mean? Is it like on the left-hand side, there are only 2 of this?
Yes.
Okay, thank you.
So this is just a singlet and triplet states. So we saw this and thought, great, this is not so bad. Let's scale up and let's try 4. So when you have 4 sites, there are a lot more frequencies. There are a lot more things you can measure. Things get more complicated, but you can nevertheless do this. And we tried this on our 2018 IBM provided quantum computer, and this is what we got. Not so great, right? This is not nearly as nice as the previous data that nicely lined up. Yeah, this is what you got out of the machine. Now, why is this? Well, there's a variety of ways of thinking about this, but here's sort of one angle. The whole concept behind quantum computers is that if I have single qubit gates and I have 2 qubit gates and I combine them in a correct way, and exactly how you do that is an open problem, then in principle, I could build any quantum simulator that I want with an asterisk. And the asterisk is there because this is not what my quantum gates look like. They're kind of broken. They are not perfect. They're, they have varying levels of accuracy. And as a result, your quantum simulator that's supposed to beautifully produce your data doesn't work so well anymore. There's also problems with the qubits. There's a variety of reasons this happens, right? But the basic idea is they're not perfect. And we have to do something about that. And so, if you go and read quantum computing papers or you go to conferences, what you see is talks about various error mitigation strategies. We've done them here. And you can work a little bit harder and say, okay, well, actually, if I work hard and I analyze my data in a proper way, I actually get this to line up nicely with what I expect. And Fourier transforms also, they kind of work and they kind of pull out the information that I wanted. So you can get around some of these issues. So it looks like at least, they might be promising tools. Quantum computers might be promising tools for solving some problems for us. But not always. You have to take some care to deal with the fact that they are not perfect and they are noisy. The word that we have for that is NISQ, which is noisy intermediate scale quantum. Okay. Let me pause for questions, actually, because I'm going to switch topics in a second, and I figure maybe there's questions on these bits for the time being.
How do you compute these expectations? Is there like some sort of Hadamard test involved?
Yep, it's exactly Hadamard test.
That sounds expensive, no?
Yes, it is.
Yeah. Okay.
Yeah. No, you're absolutely right.
Yeah.
That's part of the reason it doesn't work well.
Like moving to a different chip, like let's say Google or Jero's chip.
So
is it gonna be better?
I'm not fancy enough to have access to Google's machines, but if you run this experiment again on today's IBM machines, it looks a lot better. right?
Oh.
So we've now had they've had 4 years of development, and things look a little bit better on their end. And if you go and run something like this on Honeywell, which is 99.8 accuracy, you actually get quite reasonable results these days.
I see. Thank you.
Yeah. Okay, so I started with talking about phase transitions, and we talked about water. So water goes, from ice to some melting point to water. There's two different kinds that I haven't talked about yet. Number one is a quantum phase transition. This is not one that you find in your regular life typically, because most of your regular life doesn't exist at 0 Kelvin. But in case you were, then what you would call a quantum phase transition is a phase transition that occurs because some parameter in your system, some physics is changing. So this is a simple one where I can take a disordered magnet and I can apply magnetic fields, which is and even at 0 temperature, and I can arrange them. There's another one, and it's also a quantum phase transition. It also happens at t=0. And it's sort of fundamentally different. And the way it's fundamentally different is in the following way. If I were to look at the difference between ice and water, what I can do is I can look at some small local patch, and I can say, well, over here my ions are all frozen, my atoms are all frozen in space, and over here they're all swimming around. Yeah. And I can do that locally. I can just sort of sit in a small area and say, this clearly looks locally very different. It's the same thing here. Here I've got, if I sit on one of these spins and I look around at all my neighbors, I can see they're all pointing in different directions. Whereas here, if I sit on one of my spins and I look around, they're all pointing the same way. So I can sit from any point and I can say, aha, I am in this state or I'm in this state. That kind of a thing is called a local observable. And here, the local observables across these phase transitions are very different. There's a different kind that doesn't have that, and it's called a topological phase transition. And that's what sort of the remainder of my talk will be about. So here is a local measurement. We're measuring NMR. NMR is a magnetic resonance, and that's the thing that you measure locally. For this kind of, these are called kappa salts. As you decrease the temperature, you see that this NMR peak splits, which means locally I can see some change in what my magnetic environment is. This is a different kappa salt. And it does not do that. We still think there is a phase transition, but by making local measurements, you cannot tell that it's there. This is a different kind of phase transition that has to do with the underlying topology of the system. And in particular, the topology of the electronic wave functions. So topology is sort of new in condensed matter physics, but really it's sort of revolutionized how we think about physics. One of the very earliest ways that we found if ordered phase, some kind of topological ordered phase, was in the 80s. This is the thing that von Klitzen got the Nobel Prize for. And when you make a measurement of what's called Hall connectivity, so you apply a voltage this way, you measure the current this way, and you see what you get. And what was shown is that these things are, they come in little plateaus. And they come in little plateaus that are separated by integer numbers times some constant. Now, this is really unusual, because usually from a physics perspective, aside from things like electronic charge, your measurement can be anything. There's no reason for it to come in integer multiples of whatever, unless something special is going on. What it turns out that is going on, which we figured out in the 40 years since his measurements, is that whether or not, or what integer number you have associated with this has to do with what the topology of your wave function is. In some sense, how many holes there are in the manifold that your wave functions live on. It's not a perfect analogy, but it sort of holds. So from a topological perspective, you can take your sphere and you can deform it. And if I were to measure the physical properties of all of these, even though their wave functions are deformed, I would get the same thing. not all physical properties, but special ones like this one. The moment I make a change like this, which I cannot do continuously, right? I cannot continuously deform and make it into a whole. It does not work. Now I will get some transition from something that has an integer, say, of 0 to an integer number of 1. And I can continue that and continue to deform it until I have a second hole that pops up, and then maybe the integer is 2. So these are nice integer quantum steps in some measurement of your system that you care about. So our thought was, well, we know we have quantum computers and they are kind of noisy. So let's see if we can try and figure out some way to use physics to help us over some of that noise. There's a whole field of topological quantum computing and topological protection. It has the same words. It is an entirely different thing. So I'm not going to talk about that one. But here, it's the sort of topology of the underlying physical model that you care about. So how do we do this? How do we use quantum computers to look at topological properties?
Can I ask a quick question, Alex?
Please do.
I didn't understand why in the figure on the right side, why are these steps, these plateaus of different lengths there? At some point,
they go, in this
plateaus
case,
at
they
the
go
bottom.
as length of 1 over the applied magnetic field, kind of.
1 over the applied.
Sorry, no, sorry, hold on. This is the Hall effect. They are, so what happens is they have to do with the level spacing, how wide your plateau is. The level spacing is controlled by the magnetic field, and so as it gets bigger, the spacing is bigger and bigger and bigger. So how long the plateau is depends on the spacing between your nearby levels, and that scales with this quantity. So the larger that gets, the further apart they are, and the longer it takes for you to move on to your next one.
Okay, and each time you have like one of these local maxima of this underlying wheel function there, that's when it's.
No, so the flat parts are the different topological phases. These the diagonal parts and the associated bumps are when you are transitioning between them.
Okay.
Yeah.
Cool. Got it.
That's a whole talk in itself.
Thank you, Lex.
You got it. Okay. Our thought was, let's try and use this. So we picked a nice topological spin model. It's called the Kitaev honeycomb model. It's kind of like a Heisenberg model, but it's weird. It lives on a honeycomb. That's already weird. The second thing is that if I have these spins, they only interact by an X interaction. These only interact by a Y. These only interact by a Z. So they care about what the different components of their spins are. It is unclear to this day whether this is an actually realizable material or not, but it's a nice theoretical model that you can play with. It has different topological phases depending on where in XYZ phase diagram you are. And really, the whole reason we picked this is because it simply has this property and we know what to do with it. And the thing that we know how to do is we know how to solve this. This is a lovely paper that talks about how to do that. If any of you have ever solved an Ising model, it's the same sort of idea, but there is a series of sort of standard physicsy steps that you do to solve this problem. In case that you know what these are, here they are, but they are a series of standard things that effectively you would do on pen and paper, right? This is a problem I could assign to a graduate student, say, make this transformation, do some Majorana braiding, blah, 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 and eventually you have your answer. So what we did is we worked backwards and to say, well, okay, let me take all of these little boxes that represent some kind of mathematical transformation on my state space and build those as circuits. And this is a very natural thing to do because, well, they know how to do this in the field of tensor networks, which sort of nicely maps on the quantum computing anyway. So it was a very clear thing to do. And then the hope then was to see if I could measure the difference between these in nice integer steps, because that's what it's supposed to be. So there we went. We built our circuits. This is what you would get for 4 qubits. You have to do some braiding. It's kind of a neat idea. What you do is you take your electrons, you pull them apart into 2 different things, you braid those together and then put them back together. So we did some development for that. In case you know something about those things, they're kind of fun to play with. But in any case, Actually, let me skip through this bit because I don't want to talk about that. Okay. So now the question is, and here are the various steps. Why did I keep these slides? Okay. So now the question is, how do you go and tell that you aren't in a topological phase? Because remember, I said you can't make a local measurement. It doesn't work. So what you can do is you can take your system. In this case, this is my my 8-site bit that I can use to build my entire honeycomb lattice. I can break it in half, and I can ask, how much information did I lose by doing that? I say break it in half, and I trace out this part of my Hilbert space. I can see then, do I have a nice full description of my system, or did I lose some information in doing that? Yeah. Another way to say this is how quantum mechanically entangled are these things? How spread out are the wave functions across this space? These are all things that are sort of related to each other. And ideally then, if you make this measurement, what you're supposed to see is a step. It goes from log2 to something else. Because it's controlled by these topological numbers. So this is what we did. We took our 8-site thing. We ran it through the Majorana-Braden gates, these f-swaps, a bunch of other things, and looked at what we got for the, it's called the entanglement entropy. So this is on one of the IBM machines. The exact thing is there. It goes with the dashed lines. It goes from log2 to something else. If you run this on a quantum simulator, which you can do, you get these stars out. If we run this on this IBM Q machine, you do see a step, but this goes with the right vertical axis. So while there is a nice step, it is not this order 1 step, it is order 0.05 or something, or 0.01. So while we did get the sort of desired thing of saying, well, I would like a step that I can easily find, it is not an integer. It is not 1 or 0, which is the thing we were hoping for. Do a bit better, but in the end, you end up with the same thing where you end, and so you can sort of build your whole phase diagram up by playing some tricks, but in the end, it's still not perfect. And this is common across the field because we're not the only ones that looked at topological phases. There are some other folks that have looked at topological quantum walks, edge states, various other things. None of them really got use of this sort of topological protection. And the reason we now know is because they're still looking at local quantities instead of global ones. And so in the next little bit, I'll tell you what this means.
Did you say a word called a topological quantum walk?
What's that?
Did you say a word which is called a topological quantum walk?
Yes.
What does that even mean?
Um,
I know quantum walk, but yeah, so hopefully that's a starting point.
I think, and Lynn, you'll have to forgive me, it's been a while since I read this paper. I think what you do is you do a quantum walk under the influence of an operator that has some kind of topological encoding in it.
Interesting. Could you send me a reference?
Yes, it is Fleurin et al. 2017, but I will see if I can dig that out.
Fleurin et al. 20. Okay, that's good. Thank you.
Yeah. But okay, so to tell you sort of what our next bit is, I have to first tell you about geometry. So let's talk about this thing. That's the Earth, and it is round, as far as we know. How can we tell? So this is a question for you all. How can you mathematically tell that the Earth is round? I know mathematicians know this, but I don't know if everybody else knows this. Okay, well, there's 2 things you can do. Number 1 is you can take triangles. You can make a triangle, and you can see if all of the angles on your triangle add up to 180 or not. They normally do. You learn this in intro geometry, right? Unless you're on a curved space. For example, I can take my Earth, and I can make a triangle that starts from up there, goes down to, I don't know, somewhere over there, goes across and back up. And this can cover, each of those angles can be 90 degrees. And then I have a triangle whose angles add up to 270. This is always true. You could do this even in your backyard if you measure it sufficiently carefully. I don't recommend it. It's very difficult, but this is always true on a curved space. The other thing that you can do is you can choose something called parallel transport. How does that work? I can take a vector that starts at the pole. I can move it down to here. I can move it across, and I can move it back to the pole, and it will end up in a different direction. So this you can try, and here's how it goes. You take your hand, and your thumb is a vector. And what you do is you start pointing it backward, and you move it down, and then you move it across, and you move it back up. And now my thumb is pointing to the left, whereas previously it was pointing towards the back. And that's because this space that my arm is making is a curved space. And this is generally true. Any loop that I make, no matter how small it is, my vector will point a slightly different way. Okay. So now what does this have to do with condensed matter physics and quantum computing and that sort of stuff? Well, what you do is the same thing, right? These are not statements about spheres. These are statements about shapes of spaces. Our space, instead of a sphere, is a torus. If I'm working a two-dimensional material, it's 2D periodic. What my vector is, or one way to think about that is, or rather the change in my vector is the change in my wave function, the expectation value of the change in my wave function. And then you can ask the same question, although the question is slightly different. Now the question is, if I walk a closed loop around my torus, for example, this or that one, what kind of phase does your wave function pick up? Now, wave functions aren't supposed to be single valued. I can't at one point in my manifold have multiple wave functions. So the best it can do is pick up a phase that is some multiple of 2 pi. So e to the I 2 pi. That's the best I can do. You can sort of picture this as, and so depending on what phase you pick up, your space really has different shapes, right? If I think if this is my loop and I think of the vertex axis as my wave function, right? This is the case where as I move around, I don't pick up any phase, whereas a Mobius strip is the case where I would pick up a phase of pi. It would twist around once. Yeah. So these really tell you sort of about the shape of your wave function, specifically of your wave function bundle. Okay, so the phase is 2 pi. All right, so let's try that, right? So we can take this thing, we can go and measure it. What you do is you have to measure the wave function at 2 different points, compute the overlap, do some math. We have circuits that do that. These are still the Hadamard test, still expensive, but it's a thing that we can do. So we try this for some model. So here's something simple. It's called a chiral P-wave superconductor, but you can forget about the words and just think this thing is topological or it's not. When it is not topological, it's called topologically trivial. Here's what the phase looks, here's what the wave function sort of angle looks like. And what you can kind of see is, I can pick some path in any loop that I want, and really the angle just sort of stays in the same space. And so I don't pick up any net phase. Whereas in the non-trivial phase, if I, there are paths that I can pick where I go all the way around once as I go along. So I pick up a phase of 2 pi on this one. And so this is the idea. You go and measure what's called the holonomy, where you take one of these paths, you measure the angle of overlap, and you see if you go, around 0 or whether you go from 0 to 2 pi. So we did this experiment, and here's what you get. The blue lines are what you're supposed to get. The red lines are, runs from a quantum computer. And well, with a parent's eye, you could say, okay, well, look, this has like a thing that looks like it crosses to a different branch. And so this one, I could, convince myself that it's, topologically non-trivial, and these just sort of wiggle, and so maybe they don't. But it's not very convincing, right? This is not, again, not the clear thing we were looking for. Now, why is this? Well, what we're doing is we're taking one loop, one path, right? So I'm making one of these loops and I'm asking about this phase. This works really great if my system is this. If I have a nice spherical cow and everything is perfect. But my quantum computer is not perfect, and it measures these overlaps and it gets it wrong. And so rather than looking like a cow, it looks like one of these things. right? I get all these deformations in various places. And so if I take a path that happens to hit one of those deformations, which I will, I'll get the wrong answer. The solution to this, and this is what we did, was rather than looking at individual paths, is you look at your whole manifold. You compute the curvature on your whole manifold rather than just along paths. And the reason that works is if I have one of these bumps, it makes things incorrect along one path, but along the neighboring path, it makes it incorrect in the opposite way. And so your deformation of your wave function bundle that's made by the fact that your quantum computer is not perfect will get canceled out in sort of a clever way. So we didn't come up with this idea ourselves. We stole it from condensed matter physics, but that's okay, still worked. So a bit of math, you go over to local curvature instead. You get these potential errors that cancel on one side and the other. The punchline is as follows. We can now, by integrating over the whole manifold rather than paths, compute these integers. The integers are called Chern numbers. And here's what you get. The black line is what you're supposed to get. The red circles are results from a real-life quantum computer. And sure enough, we finally reached a point where, we actually get zeros and ones in the way that we're supposed to. So we've used the topological properties of our material, of our model, to try and to exactly have these nice measurements of 0 or 1, and are with that able to identify these topological phase transitions as I go from Chern number 0 to Chern number -1 to Chern number +1 to Chern number 0. And as far as we know, this is our first sort of exact measurements of any kind on quantum hardware. There's no rounding involved. There's just counting things. And so you get a number, and the number is either 0 or 1 or -1. Okay. We've done a whole bunch of things in this space. We've done a bit more with, I showed this earlier, really a whole bunch of different topics that we've looked at. I'm happy to chat about any of these things. There are some papers associated with it. But otherwise, thank you guys for your attention. And it's been fun.
Thank you so much, Lex. This was really an enjoyable presentation. I appreciate all the fun figures. They will definitely stick.
They are fun to find. Google Images is my friend.
Do we have any questions from the audience? We have a few minutes for questions. Feel free to unmute you and pose questions.
And I know I wasn't that clear.
Yeah. I had a quick question, which was just on the topological material side. I've always been curious, is there like a holy grail kind of simulation problem that's, you want to see or observe some topological effect, but the Hamiltonian is making it incredibly difficult? It feels like a lot of times people are doing the ones you can show by hand, and I'm just curious, since I don't really know that area, what the ones that have a lot of unknowns, and if we could do an experiment on the device and do it at 1,000 qubits or something, it would give us something.
Yes. So topological physics has benefited a lot from the fact that a lot of these systems are just nicely weakly interacting and therefore really nicely described by density functional theory. Right? Where life gets difficult is there's a good diagram for this. So a lot of topological physics relies on strong spin orbit coupling. And we know how to handle that relatively well. The problem is when you start introducing strong interactions on top of all of this other stuff, right? So then you would have something like a Hubbard model in addition to your topological phases. And that's a place I think where there's still a bunch of work left to be done. So it's like a variant on our normal strongly correlated systems, but now it's strongly correlated plus some other additional, sometimes difficulties, but sometimes help also.
I see. Is there one in particular people often call out, or is it just kind of this general class of adding strong on-site interactions or something like this to existing models?
To follow up, I think what Gerald was asking is whether there is something called a FIMOCO.
Yes.
For,
Yes. I don't.
But in
so-
this field,
No, I know what
it
you
doesn't
mean.
need to be. It doesn't need to be even exactly that, but
Yep, yep.
something.
There's okay. So this is an interesting thing. This is sociologically, this is a key difference between material scientists and physicists. Material scientists care about what the material is. Physicists just, we care about the physics it exhibits. But I would look at osmates. I would look at iridates, like some of the sodium iridate compounds. I would anything. There's like manganese silicide, but if you put chromium in it, then life gets very hard. So there's a wide variety of these things. They're not like, I don't know if there is a FEMOCO or something similar, but it's a good question, and I actually have to think about that.
Yeah, although I personally don't quite like the FIMOCO story, I have to say it's a PR success.
It
So if
is,
you can
right?
come
It
up with
sells really
something-
well.
yeah.
No, you're absolutely right.
Yeah. So
Oh, yeah.
Okay, excellent. I will defer any further questions to Lex's email inbox. Thank you very much for this wonderful talk, Lex. That's very
Thank you all for being here. I really appreciate it, and I'm looking forward to the next one.